The next area of NDT we're going to look at is eddy current testing, also known as the acronym ECT. And you can see an example of an eddy current tester there. This is what we'll be using in lab. This is from a company called Z-Tech. It's the MIS-21B model. It's been replaced. Now they have a version called the MIS-21C, which is a more capable color screen. But this is still industry standard, even though they've come out with something a little bit newer. But so eddy current testing, what it's used for, it's primarily used in aviation for two things. The first is for crack detection, and it can detect primarily surface, but also some shallow subsurface up to about up to cracks that may have occurred about a ½ inch deep. And then the other area that we use it for testing corrosion is we can detect the thinning. When corrosion takes place, a certain amount of metal is eaten away by the corrosion that forms. And so that causes the base metal, the material that we're testing, to get thinner in the areas where corrosion has taken place. And so we can measure that as well. Outside of aviation, some of the things that it's used for, in manufacturing, material and coating thickness measurements. So this can be things like, you can measure things like paint thickness, chrome plating thickness, cladding, and other platings like that. It can be used for material identification or sorting. So if a facility has mixed materials that end up getting mixed, or if there's suspected bad batch or a contaminated batch of metal parts, it can be used for that. It can be used for conductivity testing. And then finally, the kind of heat treatment and case steps. So rather than coatings or plating thicknesses, which are material added to a base metal, when you heat treat or case harden a part, it changes the properties of the outer layer of the part while leaving the inner part the original properties. And so in that case, you're able to test it as well. But again, those are mostly manufacturing uses. Our in-service uses are that crack detection and corrosion detection. So eddy current has some very distinct advantages. The biggest one is it's extremely sensitive to small cracks and other defects. And again, kind of like mag particle and liquid penetrant, this testing method has the ability to detect cracks and other flaws that are too small to see with the naked eye. Again, as I mentioned, it's primarily surface, but it can find near surface defects or backside type defects in things like sheet metal or thin metal parts. The results are immediate. There is no, you don't have any kind of like dwell times like you do for liquid penetrant. You don't really have, there's not a lot of setup involved. And like something like X-ray, you don't have to develop film, although most X-rays gone to digital detectors now. So you get immediate results. It's portable. That unit you saw the picture at the beginning is handheld. It can be handheld, or some of them can use neck straps or that kind of thing. It can be used for more than flaw detection. Again, like I said, it can be used for corrosion and other material sorting and other stuff like that. There's minimal part preparation. This can be done on painted parts. In fact, it's one of the most common methods used for in-service inspection of aircraft, and particularly aircraft skin, riveted skin, pressurized hulls, and looking for cracking around rivets, as well as spar inspections, wing spar inspections, and that kind of thing. And then finally, in some cases, the probe, you can actually set this up. It can be set up where the probe itself doesn't have to contact the part. Not as critical in aviation, but there are applications where you're not able to get direct access for some reason, but you can calibrate the equipment to work without actually contacting anything. There are some distinct limitations to eddy current testing, though, too. The first one is the material must be conductive. So it has to be typically a metallic material. Now, conductive, different than mag particle, is that it doesn't have to be ferromagnetic. Like I said, this is used oftentimes for aluminum parts, and it's often used as well for titanium parts, and so those are materials that are conductive. They can conduct electricity, but they aren't magnetic. This can be used on magnetic, ferromagnetic materials as well. So it can be used on steel. It can be used on all kinds of steel, including stainless steel. It can be used on titaniums. It can be used on aluminums. But you're not going to be able to use something like eddy current. You can't use it on something that's made out of like a composite, for instance. The surface must be accessible. Now, in the last slide, I said it doesn't have to have contact. However, you still have to be able to access it. Versus something like X-ray, where you can kind of shoot the X-rays through other things to be able to image something that's maybe hidden behind something. You do have to have direct access, but the probe itself doesn't have to touch the surface. This one does require a certain amount of skill and training, both to perform the method as well as to interpret the results. The surface finish can be very critical in what kind of an indication you get. And so rough surfaces are tougher or harder to inspect and can cause interference and false indications. And this one's different from some of our other methods, in that one thing we need here is we need a reference standard for setup. So you didn't need this for visual inspection, although you did use it with the combustion chamber. But you can perform visual inspection without having a second part to look at to compare it to. And you can perform magnetic particle inspection without having to have a reference standard or a second part to compare the one you're testing to. And you can perform liquid penetrant inspection, again, without having a second part or standard to compare it to. But for eddy current testing, we have to have a standard, reference standard, that in some way simulates or matches the type of flaw we're looking for in the given material that we're looking for. And that reference standard has to be fairly similarly constructed to the part we're looking at. So similar geometry, similar surface finish, and similar, same material, even down to the alloy level. So we do have to have these reference standards needed for setup. So it's a little bit more purpose, it's kind of got specific purposes you're going to use it for, rather than just a general crack inspection of something like a crankshaft. And then the last part here, depth of penetration is limited. So it is, again, it can do surface flaws and shallow up to about a ½ inch deep subsurface flaws, but you're not going to do anything, you're not going to find anything really any deeper than that. To do something like that, again, now you're getting into more of an X-ray or an ultrasonic testing type environment. So again, this really lends itself to surface or testing things that are thin like sheet metal. So eddy current testing relies on the principle of electromagnetic induction. And I've got a link here this brings up. It's called the Maglab Magnet Academy. And I'll try to do this slow, so hopefully it comes through on your end. But when you run this, it's just a quick reminder of what happens. So here it's shown a coil of wire and a voltmeter, and then they have a permanent magnet here on the left. And you can control the number of coils. So if I move the magnet in and out, you'll see your voltmeter will have slight deflections. If this isn't coming through great on your end, you can always click that link and do it. But if I turn up the number of turns of wire, you get a more pronounced deflection of the needle. The same magnet is going to create a greater current through the wire the more turns there are here. If we flip it, it reverses that process. Okay. So a changing magnetic field inside a coil of wire is going to induce a voltage in that wire. Okay, that's the key with eddy current testing. So that's why this test piece has to be electrically conductive, because we have to be able to induce a inductive we have to induce a inductive property into the metal. And so, but it just has to be conductive. It does not have to be ferromagnetic. You know, most wire, for instance, is copper. We can conduct electricity through copper wire. We get a magnetic field that builds up around a copper wire, but copper is not ferromagnetic. And then that final, and I've got it here in bold again, because this is one that students forget or have a little bit of trouble remembering or understanding, is that, again, this is comparative, so we have to have a reference standard whenever we perform eddy current testing. So if we look at an inductive circuit, you know, an inductive circuit in this case is now, instead of detecting a magnetic field, like I showed in the previous example, this is developing a magnetic field. So if we take a voltage, and in eddy current testing, it's going to be an alternating current, because we always want a changing magnetic field. The voltage in a coil or a wire stops or is only present when the magnetic field is changing. Either you're moving a fixed, like a bar magnet, a permanent magnet through a coil, or you're running an alternating current through the coil. So an AC voltage source is run through an inductor, which is essentially a coil of wire shown on the right here. And that is going to put out a magnetic field or a magnetic flux. And so what we can do is the next step is we kind of put these together. We measure what's happening in that coil as this flux is changing. And to understand that, we got to understand what's going on in an inductive circuit. So there's three things that that kind of make up induction and how they go together. So inductance is current carrying coils produce a magnetic field, which produces its own current flow. Okay, and this is how like a transformer works. A coil next to a coil, you're going to that will. And that's given by the units of inductance are henries. So you'll see inductors are rated in henries. That's how much inductance they're gonna exhibit. The symbol for that is L. Now, in addition to that inductance itself is going to, when you run current through the wire, it's going to build up a magnetic field around that wire or around that coil of wire. That magnetic field is then going to try to send a current back into that same wire. Okay, so you know now you've got a magnet now. So first you're creating a magnetic field. You're running current through a coil of wire that creates a magnetic field. Well, that same magnetic field is going to react back on the wire, and it's going to try to create a current in that wire that's already got the current, and that's known as inductive reactance. So, or it's an induced current. So that induced current is 90 degrees out of phase with the initial current, the initial alternating current. And so what that's going to do is, at the points where it's out of phase, especially those spots where they are opposite current, you know, where that alternating current, that AC wave is opposite, which will happen when they're 90 degrees out of phase, you're going to get resistance taking place. It's going to oppose the flow of current through the inductor. And that's given by the unit ohm, similar to a resistor, but the symbol is X sub L. And then the other thing you're going to have is in that wire itself, you know, any kind of conductor is also going to have a certain amount of resistance or impedance. And so that's what's shown here. So if we take what's called the vector sum of the inductive reactance and the resistance of the wire, that's going to give us the total resistance of the coil. It's also given the unit ohm, but it's shown by the symbol Z. So the impedance is going to be Z. And what we're going to use is these three things as we move objects, metallic objects, closer to or away from, or put more metal in front of, or remove metal in the form of like a crack that's in front of a coil. That's going to change the inductive reactance, the inductance and the inductive reactance. And that change we can measure, and it can be used to indicate when there's a change, when the amount of metal in front of a coil changes, or if there's a crack or corrosion. So here's that diagram of, here's the voltage and current. This is when they're in phase. This is just running through wires. So when we run it through a coil, this is what happens, is that inductive reactance gets out of phase of the original current. And so you can see here there are points where they're going to oppose each other. So for instance, at this point here, oops, I can draw a straight line. At this point here, the voltage going in and the inductive reactance coming out are opposite. One's positive, one negative. And so ultimately that's going to basically cancel out. And for a split second, the voltage coming out, or what we see coming out of the coil, is going to be zero. And then you'll get the same thing over here, over to the right, where again, in this case now the voltage is negative, the induced current is positive, and so they're going to cancel each other out. So that's going to act, that's why it acts like a resistance, because it's going to reduce the voltage going through that coil. So that gives you your inductive reactance. And so what we do with that is we sum that with the actual resistance of the coil itself to get our impedance. So a vector sum of inductive reactance and impedance. And when you add those together, it looks something like this. So here you can see they've got the inductive reactance on the on the y-axis, the resistance on the x-axis, and so the ultimate impedance is this vector sum z between the two. And as we change the impedance of the coil, and we do that by changing what conductive materials are near that coil, it's going to drag the tip of this impedance line, the tip of this arrow, around on the diagram. Now our diagram, our testing device, isn't always going to have the inductive reactance on the y-axis and the resistance on the x-axis. In fact, we can rotate it. But what we'll do is try to rotate it so that our indication on the screen. So here is the screen from one of our testers. And this is showing the XY plane created by plotting. And this plots lines over time. So these three lines here, in each case, they started at what's called our origin point down here at the right. And we went over three different size cracks. We'll call them 1, 2, and 3. So crack 1 is the smallest. It has the smallest change in the amount of metal in front of the probe. 2 is somewhere in the middle, and 3 is the largest change, the biggest crack, biggest change in amount of metal in front of the probe as we move the probe across a crack. And so as we move this probe across, in this case a crack, it's going to change that resistance vector and inductive reactance vector, and it's going to change where it ends up. And so it plots these points over time. So as we move it, and so as we move the probe along, it's going to change where it plots. And then what happened with each of these is we moved it over a crack, it came out to the tip, and then it worked its way back to the middle as we got clear of the crack. So same thing with number 3. It's going to work its way out to the tip over time, and then it's going to work its way back to the origin as we go past that crack. Okay. But just understand that in this case, Y is not necessarily inductive reactance, X is not necessarily resistance. We can take the screen and rotate it any direction we want to make it fit the screen and make the indications most obvious. And so what we're looking for is if we're moving our probe along a part that's not cracked, and if this part was not cracked, or areas that weren't cracked, our indication on our screen would just show up as a little dot right here. And then if we come to some kind of a flaw indication, that's when you get one of these lines that shows up. And so that's why we have to have a standard, as we compare what we see on the screen to what we got on our standard.